Hello and welcome back to Calculus 2. We are starting chapter 11 on power series. So we are going to take a look at Taylor polynomials eventually and see what is so special and why these are used so much by electrical engineers and others as well. But basically, these power series drive a lot of our applied mathematics to give us all of the modern physics and engineering and all of that good stuff. Now, we first have to see what these power series are and what they look like. Take a look at some convergence, do some calculus, so that you can apply them in differential equations. Sure. It's this button right here. So we are going to start by saying the sentence that power series contain independent variable x. So power series are series which contain independent variable x. Power series centered at x equals 0 look like this. Summation Cn x to the n from 0 to infinity. And we are going to write this out as when n is equal to 0, we get C0, x to the 0 is 1, so don't worry about it, plus C1x plus C2x squared plus C3x cubed plus C4x to the 4 plus ... going forever. It goes to infinity. Is this a polynomial? No. Polynomial has to have x to the n. It has to have the highest term. Over here, you don't have the highest term. You can call this an infinite polynomial, but it's not a polynomial in a sense you know it, because your polynomial from before is either a constant function, like y equals 3, or y equal mx plus b, which was a linear line, or quadratic, or cubic, right? But they were all finite. This puppy here is infinite. You can't talk about leading term. You can't talk about leading term coefficient. You can't talk about the order because there's no highest exponent, right? Quadratic is of order 2 because x squared. Highest degree is 2. So polynomial of order 2. So power series is this continuation of polynomial into infinity without having a leading term, without having the order, without having, right? Not the order in terms of ordering terms, order in terms of what is the degree of the polynomial. Now, another one, the one that we will see much, is power series centered at x equals a. Now that's the boss. Summation 0 to infinity Cn x minus a to the n to give us C0 C1x minus a plus C2x minus a squared plus C3x minus a cubed ... going to infinity. And I am going to put this one on a cloud, even though the other one you are going to see a lot of it as well. But generally for calculation and much of your engineering stuff, you might be using the one that is centered at A. Well, I mean, you can put A equals 0 and you just get the one on top. Now, we will understand this business of centered at A later. Let's focus on few power series. Say you have power series 0 to infinity. Say you have n minus 1 times x to the n plus 1. You can have that. It's okay, right? And the way you will deal with this is when you plug in 0, you will have 0 minus 1 is negative 1. Times x plus 1 minus 1 is 0, so this term dies, plus 2 is going to be 1x to the 3, so x cubed, plus 3, that's going to be 2x to the 4, plus 3x to the 5, plus dot, 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 going forever. So you see that we started with the negative x, and then we go x cubed, x4, x5, and so on. Power series, you got something that resembles a polynomial, except it's infinite. You can't forget that piece. Summation of x to the n divided by n factorial from 0 to infinity. I will write this one more time in blood over here. 0 factorial equals to 1. So we get 1 plus x squared over 2 factorial plus x cubed over 3 factorial is 6 plus x to the 4 over 4 factorial 24 plus dot, 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 going forever. When you have power series, you're going to have x to the n, or x to the n plus 1, x to the 2n, x to the something, right? It has to be x to the n of some sort, and then this coefficient in front can be something else. So power series, as you can see, give these polynomials, infinite polynomials on the other side. Is this the end of the story? No. There are binomial series. There are Fourier series. Did anyone hear about Fourier series? They have sines and cosines inside. They're awesome for signals and things like that. Electrical engineers and computer science graduate degrees. Hello, right? So you're going to have a lot of those. Complex domain contains Lorentz series. Complex domain meaning I equals square root of negative 1 and so on. So we are scratching the surface here with Taylor series, which are the polynomial series. And we're going to learn how powerful those are and what they're used for. But as I said, there is so much more later on.
From one of the labs that we did, that x to the n over n factorial, is that
e to the x?
X.
Yes. Okay. You already know that. You're halfway there. Good. What he recognized is that this over here is e to the x. Nice. Boss move. All right, let's go and talk about something that's called Taylor series, which are power series with a specific coefficients that have, and it has specific purpose. This is the big deal over here. Welcome to being 200 years behind current mathematics. As we write this title. That's okay, you catch up about... You used to catch up like 200 years and then 100 years, and now you're catching up in like spans of 50 or so. So we have Taylor series. Taylor series are defined as summation Cn x to the n, well, let's do x minus a, to the n, from 0 to infinity, and Cn is the nth derivative computed at a divided by n factorial. These two together create Taylor series. Now you might be going like, yeah, so what? Hold on. It has already been noted that that polynomial was e to the x. E to the x equals some kind of infinite polynomial? That's a new concept. But it's also a very powerful concept. Yeah, e to the x is easy to differentiate and integrate and all of that stuff, but so are polynomials. And I hope that you are beginning to understand what is so powerful about this. We are about, get hyped, we are about to turn any function into a polynomial and just eliminate all of the calculus and rules and everything you learned so far and just differentiate and integrate those. Yeah, there goes your year of study. Nowhere. Right? No more product rule, no more quotient rule, no more chain rule, no more nothing. Right? It's just going to be, oh, I just have to differentiate or integrate the polynomial. Awesome. And over there you had like e to the 17 sine x's and stuff like that. So f of x equals sine x. Move that into Taylor series. So how do we achieve this? Well, my coefficients here are derivatives of the function computed at a. Oh, I'm gonna center at x equals 0, so a is 0, just for the beginning, and then we'll figure out what that means. Okay, sounds good. So we're going to do this. This notation here is the nth derivative. You are used to prime and double prime and triple prime, but as soon as you hit the fourth derivative, you put 4 in parentheses. So pay attention to notation. F prime of x is cosine x. F double prime of x is negative sine x. F triple prime of x is negative cosine x. And the fourth derivative, there's your notation now, with the 4, is going to go back into sine x, and it's going to start to loop. Fifth derivative, of x is cosine x. I'm going to regret putting all of this there. Is negative sine x, and that is going to go forever. So, what do? I compute all of the f of zeros. I have f prime of 0 is 1, f double prime of 0 is 0, f triple prime of 0 is negative 1, the fourth derivative at 0 is 0, the fifth derivative of 0 is 1, the sixth derivative of 0 is 0, and it's going to go like that. 1, 0, negative 1, 0, 1, 0, negative 1, 0, and so on. Forever. Let's put the polynomial together. summation of the derivatives computed at 0 divided by the n factorial, 0 to infinity, x minus 0 to the n. It does nothing. Cool. First is 0. Zeroth derivative of the function is the function, right? Because you haven't done anything. And then you have first derivative and then the second derivative. And those of you who are interested in mathematics, look up the half derivative and stuff like that. Yeah, look it up. So the first term is f of 0 plus, when n is equal to 1, I have the first derivative computed at 0 divided by 1 factorial times x to the first power, plus second derivative computed at 0 divided by 2 factorial times x to the second power, plus, now n is 3, third derivative computed at 0 divided by 3 factorial x cubed, plus fourth derivative, notation changed, divided by 4 factorial x to the 4. I have 2 more. F to the fifth derivative of f computed at 0 divided by 5 factorial times x to the 5. Plus sixth derivative divided by, sixth derivative computed at 0 divided by 6 factorial x to the 6. Plus dot, 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 it's infinite polynomial. Did we just compute all of these values? Yeah, we did. Sine of 0 is 0. Plus 1 divided by 1 times x, plus 0 divided by 2 factorial is 2x squared, minus 1 over 6 x cubed, plus 0 over 24 x to the 4, plus 1 over 120 x to the 5, plus 0 over 720 x to the 6, plus dot, dot, dot. I just computed everything. X minus x cubed over 6 plus x to the 5 over 120 plus dot, dot, dot. What was this? Sine x is equal to that. So what we just got is that sine x can be written as x minus x cubed over 6 plus x to the 5 over 120 plus dot, 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 going forever. Ooh. We just replaced sine with the polynomial. Cool beans. Now, what's the sine of 3? Sine of 3 radians, that would be a living nightmare to compute, or sine of 2 radians, or sine of 18 radians, right? When you have sine of some number radians, you can have pi over 2, it's okay, right? But if you have something that it's not in the divisions of pi, wouldn't you like to compute 2 minus 8 over 6, right? Plus 32 over 120? That would be nicer than computing sine of 2 using linearization and differentials, or differentials, right? So we just turned the sine into this polynomial. Now, some of you might have spotted this. Why would I circle that? Did anyone take physics ever? Where the teacher says, this equation is a nonlinear annoying equation, so for sufficiently small angles, we're just going to replace this sine x by x. Yeah. One term approximation. Probably your head just exploded at that point, right? Because you went, what the hell? What do you mean replace sine x by x? Could I have just passed my whole pre-calc 2 doing that and just eliminate all the trig forever, right? Like, imagine just killing all of the identities, killing like a complete family of functions, right? Along with all the calculus. So what I'm going to do now is I'm going to do some of this graphing over here. So our target function is sine x, which is this red wavy line, right? We all like and respect. And now your physics teacher said, I can just replace it with x. How's that the same? It's not the same. But hold on. He said for small angles, right? If I stretch this so that you can only see the first quadrant, which is from 0 to 90 degrees, which is the bump on sine, okay, my pi over 2 is about 0.7. I mean 0.57. 0.57, really? 0.57 is here. That's about pi over 4. The y values are extremely close, right? That's pi over 4. Look at the pi over 6. They are pretty much the same. So from negative pi over 6 to positive pi over 6, which is this much, the blue line and the red line are pretty much on top of each other, right? Now we are going to add the rest. X minus x cubed divided by 6. And then I have plus x to the 5 divided by 120. Ooh. Look at the green line. Do we all see how green line matches the red line much longer than the blue line? The more terms I put in, the more the function is going to snake around x, the sine x. It's going to match it for longer. I only used 3 terms, and I pretty much mapped the entire first quadrant from 0 to 90. Right? 2 lines are almost on top of each other everywhere. If I add one more term, it will get better, and it will match it even further. So I'm going to go minus x to the 7 divided by 7 factorial. Look at that. It almost matches 0 to pi. Pi is right here, 3.14. You see that the red and green are barely off? This means that instead of me calculating any values in sine x, I get to calculate them in that polynomial. Right? Right. So this is what the power series are. They take a function that generally you don't want to compute, you don't want to differentiate, you don't want to integrate, right? and they turn those into these polynomials. And then you compute with those. Easy to differentiate, easy to integrate, and easy to plug in the value. Living nightmare to find roots. Living nightmare to find roots. But the rest of the stuff is easy. So there's never a free lunch. You know? So, going back to our lecture, if you dig deeper, you will actually find that it's better, instead of 6 and 120, to put 3 factorial, 5 factorial, and then 7 factorial, 9 factorial, with a sign going plus, minus, plus, minus, plus, minus, plus, minus. And then you say, oh, there's a pattern of odd numbers, and there is also alternation. We can stuff this into a single summation, right? And that is where you get the formula that sine x can be written as the infinite polynomial 0 to infinity, -1 to the n of x raised to the 2n plus 1 divided by 2n plus 1, minus 1, sorry, factorial. 2n plus 1 for the 0, right? When you plug in 0, 2n is 0, and then plus 1 is 1, so you get your x. Okay, good. We were able to mush the entire infinite polynomial into single summation. And then you pick how many terms you want to keep. You already saw that 4 terms cover the full period. We don't need the full period. You need just 0 to pi over 2. That's the first quadrant. That's what the principal angles are, or reference angles. So 3 terms is enough, instead of dragging the sine. Now, if you don't need anything more than 30 degrees, your physics teacher said, just use x, right? So now this becomes a formula for sine. Can anyone see something interesting about this formula? Something that you learned as a property of sine all the way back in your pre-Calculus 2 course when you talk about trig. They said just memorize these properties. What type of function is sine? That's called periodic. Yes, that's not what I'm looking for, but that's true. It's periodic. Odd function. Sine was odd function. You had to memorize that. Do you need to memorize it now? Look at it. What are the exponents? All of the exponents are odd. What's the derivative of sine? What kind of function is cosine? Even. And what happens when you take derivative of each one of these? They all shift into even numbers, right? Oh yeah. I know. The whole math just clicked in one spot. And some of these things that you were asked to memorize before, and they made the argument, oh, it's symmetric on y-axis, it's symmetric on y=x-axis, and all of these kind of things, right? You had to memorize that thing because this was not available. But now, it's clear as a day. You look at this and you say, oh, all odd powers, sine is odd.
It's tailor fit to sine.
Yes. Nice. Tailored fit sine. I like it. I'm going to go over the procedure one more time. Well, let's do it one more time by working out one very difficult function, e to the x. So f of x equal e to the x, centered at 0. We still have to talk about that. Leave it alone. And let's see, the first derivative of e to the x is And how about the second derivative of e to the x? And how about all derivatives of e to the x? e to the x, right? So all of these computed at 0, right, all of the derivatives computed at 0 are just going to be e to the 0, which is 1. Awesome. All right. Remember that we have summation of our function computed at 0. Those are all ones. Divided by n factorial. And then x to the n. So what do I have? E to the x is equal to what? It's equal to 1 divided by 1 factorial times x to the 0, which is 1, plus 1 divided by 2 factorial. No, lies. This is 0 factorial here. This is 1 factorial to x to the first power, plus 1 divided by 2 factorial x squared, plus 1 divided by 3 factorial x cubed, plus dot, 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 because we got lazy. So e to the x is equal to 0 factorial is 1, x to the 0 is 1, and 1, so they all work out to be 1, plus x squared over 2 factorial, plus x cubed over 3 factorial, plus dot, 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 and there is your polynomial for e. Cool? Keep first 3 or 4 terms for a good approximation. Now, compress all of this into a single summation, 0 to infinity, to get what? X to the n divided by n factorial, and that becomes your Taylor series, power series, infinite polynomial, Taylor expansion, all the same names, for e to the x. Shall we do the preview of 11.4? Now that we have these two? Remember that one?
Yeah, that was.
How about a 3 polynomial times 3 polynomial? You FOIL 2 polynomials and then integrate?
Still sounds terrible.
Yeah.
Sounds way better than
No, I think you will make it better.
Evil is better than foiling polynomials?
Yeah.
Yeah, at this point in life you have options. It's like when you go to the supermarket, right? And you need to buy toothpaste, but there is a wall of toothpaste, 15 different brands, and each one of them has like 15 different types, so that's 15 squared. And you're just like looking at it and you give up and you never buy one, because, right? So now you can either do all of the calculations, which is the integration by parts twice, and then move the term and divide by 2. Remember that? Of course you don't, right? Or write a 3 polynomial for e to the x, 3 polynomial for sine, let's say 3 terms. Foil those, you're going to get 9-term polynomial, and then integrate 9-term polynomial. Pick your poison, right? Pick your poison. So that's your 11.4, right? So we don't have to deal with certain things we used to deal before. All right, cool. Now, what I want to do is discuss this business of centered at 0, centered at 3, or centered at 7. So when I start centering these polynomials, what they do, because I am subtracting directly from x, I am shifting them left or right. That's all I'm doing. Now, why is that important? If we go back to our sine over here, we notice that I don't care which approximation you look at. Red line is the sine original, and then you have the blue line, which is just x, and you have the green line. So I really don't care which one you look at. The further away you are from the zero, the more error you have between the y values. How much error do you have at zero? Zero error, right? And the reason is it was centered at zero. And because it was centered at zero, these functions follow original function the best around the point where they're centered. So if I want to find a value of, let's say, 7.3 for sine, you know the rule. Desert island, Wilson's gone, calculator, cell phone, all dead, right? And you just need to find 7.3, sine of 7.3. You will center your Taylor polynomial at 7. And then just compute, right? Because at that point, right, they're going to be very close. So what I want to do here now is say sine of x minus 7. And now this is going to be annoying to change all of it, but such is life. I am going to introduce this idea of minus 7 everywhere, which is going to shift. Do you see that all of my functions left? I'm like, bye. We're not there anymore. But you know what's going to happen when I scroll and I put 7 into view, right? They're all going to be there. And that's the idea of centering. Oh, something is...
The red one. But sine x minus 7.
You haven't changed sine x yet.
Maybe if I type things right. There we go. They're all at the pile. This time they're all at pile at 7, right? So the idea is that you center your expansion where you need to do calculations. And then you go from there. So now I'm going to ask you to compute one of these Taylor polynomials on your own, right? You saw me work on sine, saw me work on e, right? I took care of those difficult functions for you. And now you get to try something like ln of x plus 1. And let's center that at 2. Guys, that means you want a 2, you want a 5, you want a 6, or 2 is good? 2 is fine? All right. Because I need to make sure you're happy. Okay. So let's see what you get when you transform ln x ln x plus 1. Bye. By the way, what you're doing now is 10.3. And they did a couple of these About 4 terms should be enough. If you did 5, I mean. Did I get these right? Thank you. Now we need to divide each one by the factorials and put x minus 2 to the n. So ln of x plus 1 is going to be ln 3, that's the 0th derivative, is the original function, plus the first derivative, that's 1/3 divided by 1 factorial x minus 2. Second derivative, that's 1 over 9, 2 factorial 1 over 18. You know what? I was going to write it out. 1 over 9 divided by 2 factorial x minus 2 squared plus 2 over 27 divided by 3 factorial, which will be 6, x minus 2 cubed, minus 6 over 81 divided by 4 factorial, x minus 2 to the 4th, plus dot 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 going forever. That's ln 3 plus 1/3 x minus 2 minus 1 over 18 x minus 2 squared. Now 3 factorial has a 2 in it, so that's going to cancel. So this is going to be 1 over 81 and then we'll have x minus 2 to the fourth plus dot dot dot. Now this fraction is 681 times 1 over 2 times 3 times 4, kill, that's 234, 324. 324 and then 1.
Actually, I have a question. Should that be x minus 1 instead of x minus 2 because it's log? It's log x plus 1.
No. It's x minus 2 for the expansion if you're centering it at 2. Any function can be used. It's just for the purposes of calculation. Easy peasy, not a problem. Let's see. We're going to start with sine and cosine because we already know those. We've seen them. All odd exponents with alternation for sine and cosine. Cosine is even, sine is odd, right? Look at the hyperbolic sine and cosine. What's different?
It's always that.
It's absolutely
Yeah. There's no alternation. The difference between sine and cosine hyperbolic, just no alternation. Same formulas. So half of your second order complex values floating about, you will get sines and cosines for wave equations, and all the exponential based ones will have hyperbolics in it. So that's going to help with your chapter 2 and chapter 3, obviously, with power series. So you know those, as you can see. So sine and cosine, those are easy. And part of you that is saying, oh, do we have to have those stupid factorials? Can we just have 1 plus x squared plus x cubed? Yeah, we can. And that's going to be this. Look at the first row. 1 plus x, no factorials. And it's that. And we say, well, could have been be a plus there, please? Sure, it's right here. And it's the same except it has alternation. They're like all there, right? They're so close. This is, by the way, page 740 in your textbook. This list. Do you have to memorize these? No. Are you going to differential equations? Some of them, yes. It's going to make your life easier. Page 740 in your textbook. If you want to make your DPQ life easier, you really want to know sine, cosine, hyperbolic sine, hyperbolic cosine, e to the x. Like those 5 should be right. The rest, you know, not a big deal if you don't know the rest. But they're not that difficult, and you've seen, and I hope that you guys see how the exponent, like 1, 1, 1, 3, 3, 5, 5, 2, 2, 4, 4, 1, 1, 2, 2, 3, 3, 4, 4, 5, 5. They work very well. And the formula that you are using is also having that pattern, because you have f to the nth derivative divided by n factorial times x minus a to the n. It's always n. So it's the first derivative 1 factorial 1, 2, 2, 2, 3, 3, 3, 4, 4, 4, right? They're always the same when you are grinding through the formula to figure this out. So what can you expect on your exam? Find the Taylor series. Find the first 3 terms of the Taylor series for function. What do? You take, for 3 terms, you take 2 derivatives, because the first term is what? Your original function, at a. Then the first derivative at a, second derivative at a. 1, 2, 3 terms, right? You will take 2 derivatives. That's like a second derivative. And then you will have the first three terms. We already saw how powerful are the first three terms. Now, you know how powerful they are from the Calc 1, the first two terms. Do you remember your linearization tangent line formula from Calc 1, the infamous LX? You remember that one?
Yeah.
Here it is. Calc 1, linearization. And we had L of x is equal to f of a plus f prime of a x minus a. You remember that? How about if I just write f to the 0 to the first power plus f double prime blah. Aren't those first two terms of the Taylor series just the basic linearization tangent line you guys learned? And if I am to go back, what is the blue line? It's the tangent line at 7 in this case, right? Yes, right? Tangent line at 7. So, what we just learned is this approximation that takes your one-term linear approximation from Calc 1 and pushes it into infinity to make the exact match for a function, but write down the infinite polynomial rather than, truncated linear or something. This stuff is absolutely insanely awesome. I don't know. If you don't think like it, just stand on emotion. Whatever.